Dear colleagues, I will present you a work with name From Component Failure to Hydraulic Engineering Complex System Safety. The authors of this work is Professor Marko Ivetić, UNESCO Chain Water, Faculty of Civil Engineering, University of Belgrade, and Alexander Šotić, me,
Just a little bit louder if you start, please.
School of Civil Engineering. We have one message. Our message is that complex systems, we will talk about complex systems, could fail without component failure. And in addition to that, safety is an emergent system property which occurs in interaction of system components. So our presentation is about that. So this is message, and the rest is just commentary. So outline of the commentary is a few words about complex systems, then systems thinking and systems theory, risk and safety. Those are different concepts. STEM and STPA. This is methodology I will talk about. Few case studies and epilogue. So, in addition to a message, we also have a motto, which are leading sign in the last few years. It's actually words of our Professor Nancy Levison from MIT. She said the first step in solving any problem is to understand it. We often propose solutions to problems that we do not understand, and then we are surprised when the solutions fail to have the anticipated effect. We came from hydraulic engineering area, so this presentation is primarily related to that, but anyway, it should be imposed to any kind of complex systems. We are focused to water systems, complex hydraulic engineering systems. Those systems are extremely complex. You know, we have catchments, we have surface water reservoirs, we have many gravity mains, we have river channels, we have water treatment plants, distribution network, etc., etc. It's really complex. In addition to that, usually that systems are bureaucratically divided in water resource engineering and communal services. But the system is one. Yes, and when we are trying to find the component failure, we will chase in the tail. So many component failure could occur, so how we can approach that kind of complex systems. Possible approaches, for example, traditional analysis, which is based on decomposition or analytical reduction. We just split the system in parts, in components, and in that context, behavior of the components is the same, both when they are analyzed separately or with their role in the system in totality. This is traditional kind of analysis, and some other approaches that with basic ideas of systems thinking and systems theory. The analysis starts with the system as a whole, not with the parts. Related with previous approach, individual properties of system can be adequately treated only as a whole, taking into account all aspects of them, from social to technical, because plenty of layers are in that kind of complex systems. Such properties of the system arise from the relationships between the parts of system and how those parts are fit into the whole. So the components of the system are not aware of functioning the system as a whole. A few words about system thinking and system theory. water resources management system are systems of organized complexity. They are open type, hierarchical, social, technical, require control to be adaptive, safe, and resilient. It should be noted that reliability is not the same as safety. Reliability refers to the components, and safety refers to system. Safety is the emergent system property, which is formed in the interaction of system components. So when it comes to risk, this is different than previous concept. The probability is not appropriate measure for system of organized complexity, which water systems are, because it does not take into account several very substantial elements: errors in design, social and organizational factors, adaptation of system over time. So I will not elaborate these basic approaches, but just to mention Professor Rasmussen, the concept of system migration to the state of increased risk for complex adaptive systems. Professor Wood's concept of sharp end, blunt end, and just want to underline that we need to address safety as much as earlier in the system development through all life cycle phases. And we come to control and systems theory. When some want to control some system, the controller must have a goal, must have a system model, some perception of system. He must be able to affect the system, and he must be able to determine the state of the system. In those simple 4 lines, we come to this scheme. This is a basic control loop based on control theory, and when that basic control loop extends on our complex system, we can get this kind of scheme. This scheme represents social technical systems in some organizational life cycles, and through the whole system hierarchy from the highest to the physical level. All previous is the basis for the methodology of Professor Levison. Actually, one is a concept and other is technique. System theoretic accident model and processes are based on the concept of systems theory, control theory, and elements of cognitive engineering. Basic concept of the method of the approach is constraints, control loops, and process models, and also levels of controls. You could see that in previous slides. I will not elaborate that in detail. And technique, which is based on this approach, is system theoretic process analysis, which is hazard analysis tool technique, basis for the efficient integration of results into the system processes. And actually, it is accident causality model. What are the results of this approach and technique? The result is determination of causality of causes of possible undesirable outcomes in order to reformulate those identified causes in safety constraints, which should be imposed on system behavior. Few case studies, just to tell that this methodology is applied on functioning of NASA. In Turkey, for example, when we are speaking about infrastructure, it is implied on in national mining industry system design. In Australia, it is implemented in national traffic system safety design, and but in our research, we apply that methodology in preliminary way on water supply system of the system of Užice, reservoir Užice with dam, small hydropower plant and water treatment plant, and on hydropower plant Pirot, extended with hydropower plant Đerdap. So in next two slides, we will I will give some details of these two case studies. City of Užice, what was the scene? About 10 years ago, yes, system experienced cyanobacterial bloom, potentially toxic bloom in reservoir of Ruci in end of 2013, and population of Užice lack drinking water for more than 40 days. So this is very complex system. How we can find the cause of that, whether bacteria was that or some other causes. Under the urgent procedure, some decap water intake was activated from other municipality, and the water treatment plant was reconstructed in the wild. When we applied this methodology on this case, we identified accident causes, and I will list just a few of that causes. And after analyzing those causes, the safety constraints as a result of that causes must be applied on system in order to have to achieve safety of system. So few causes are that different definitions of water source in few water regulations. So no appropriate monitoring was established at all. This is a very huge result, which have to be corrected by changing the law. So this is one of causes as accident occurs. The other, for example, city of Užice handed over to State Water Directorate reservoir of Ruci, but that directorate did not accept it. So no one managed the reservoir for surface water formally. I will not read all of that, but just for example, searching for the immediate cause of the accident and to blame the human error is an enemy in improving system safety. I did not say at the beginning that, of course, the general manager was arrested the same time, the same day when the accident occurred, but it is not cause actually of the accident. The other example is hydropower plant Pirot. What is the scene of system accident? Excessive high flows of icy water in Nišava river caused the 2 fatalities, and also devastated river environment and many hazards for river swimmers from hydropower plant Pirot. We implemented the methodology on this case. It identified that unusually low levels in Zavojsko Lake are within design limits, 22 meters low levels, but those levels are appropriate by design, they are above minimum level from design. So that could be characterized by design flow. Scheduled annual hydropower plant production plan reached already in April. Annual plan reached in April. So is it something wrong with planning? State water inspection stated that hydropower plant has a proper water permit operation according to the law. So many of bad things occur, but this is everything okay. Concluding this short case study, safety constraints have to be re-examined after complaints and fatalities. Design limits and parameters were relevant only for design phase, which is 1977, 1983, and also have to be adapted on the basis of the as-built and present condition. So, some kind of epilogue: system can only be safe if we design it safe, make it safe, and control its behavior. The STEM STPA methodology is a solid basis for leading the design, development, operation, and maintenance of our complex system, which means in addition to technical, there are also design errors, human and organizational factors, and interaction of system components, flaws related to legislation and regulation, decision makers, operators, changes, unidentified or out of range environmental impacts, black swans, etc., which would be covered with this STPA and STEM methodology. The safety of complex system have to be analyzed in an integrated, holistic way, taking into account all their relevant characteristics, not just component failure. Integration has to go beyond the physical scale of the system. For example, river basins approach to include higher administrative organizational levels, communication between different hierarchical levels and different system components and affected stakeholders. So, two recent examples with more or less obvious system accidents have revealed several design, organization, and communication flaws with any component fails. So this is significant that the system failed without component failures. So thank you for your attention.
Thank you.